Hello, I'm Theo, your quantum group professor. Today I'll talk about quantum permutations and quantum rotations. That's a very interesting subject. It's a lot of nice combinatorics there. I mean, really symmetric groups, and we'll have also some analysis like Poisson laws, things like that. So let's find first this presentation. Here we go. Oops. Oh, this will be it. So as you could see, one interesting things there, a lot of formulas. We'll have some fun with these quantum permutations, that's for sure. So yeah, let's go back first to what we did last time. So that was really a kind of tough lecture, and well, these are things that somehow things go sometimes. So we did two things. First, we established this Tannakian duality correspondence between Voronovich algebras and tensor categories. So in one sense, the correspondence is very simple. So associated to a Voronovich algebra A are these home spaces between the powers of the fundamental representation. So that's a category, obviously. In the other sense, from algebras to between algebras, okay, from categories to algebras now. Well, it's very simple too. So imagine that you want to construct an algebra satisfying this. So of course, it must be a quotient of C of n plus, right? And then the relations that we have to put is just these relations. I mean, for any t in your tensor category, you must say that t intertwines uk and ul, right? So that's what's written here, very simple. So the category must be part of this thing here, the tensor category of A. So these are just relations. I mean, there are infinitely many of them, and depending on KL, which are colored integers, right? Because you have exponents for u, but it's just no matter. It's not a problem that there are infinitely many, because every time you divide by a relation, delta epsilon s factorized. So you divide by many of them, and that's the construction. Okay, so on paper it looks very simple. So from A to C, very simple correspondence. From C to A, very simple correspondence. Now, of course, you have to prove that these are inverse to each other, and there are many proofs. And yeah, the one we had last time is quite tricky. I'm using a lot of like the deconcomitant theorem finally, and yeah, that was quite fun. Now, as an application, or main application of this, so what are the simplest Voronovich algebras? We don't know. What are the simplest tensor categories? That is doable, because you see you have these spaces of linear maps. We have to think what are the simplest linear maps somehow. And for instance, that what do we have in the category? We have these identities, of course, and you have the duality map. One goes to some of I tensor I, and that's what known as a semicircle. So here, let's somehow into diagrams. So the simplest tensor categories should be those coming from diagrams, right? And that's what we call easiness. So we take a category of partitions. What does this mean? So you take for any KL, color integers as usual, you take K here points, L points here, and just a partition represented as a picture. So picture means that the elements in the same block are connected by strings, right? And well, these things, I mean, you can compose them, right? You can put them like this. It's a kind of tensor product. You can compose like this. It's a kind of composition. You can also flip the diagram. That's a kind of evolution. So if it's stable under this operation, it's called a category of partitions. Now the theorem says that given such a category and given an n, you can construct a quantum group Gn via the following formula. So what does this mean? Here on the right, well, because these are category, these things from a tensor category, So by Tannaka duality that we had on the previous slide, there must be a quantum group satisfying this. Okay, so this uses Tannaka duality. When I say via the formula, it means that once you see this and you know that it's a tensor category, right away by Tannaka you'll get your quantum group like this. And well, the maps. So here is the formula. I mean, if you think a bit at how, for instance, the identities must correspond to the identity maps, and partitions must correspond to the identity map. This to the semicircle, and for instance, the crossing must correspond to the flip, and you get this formula. It's not complicated. So technically here, yeah, Ionian is the basis of Cn. So that's how an input tensor gets to an output tensor. It's just a sum of Kronecker symbols, and the symbols are 0 or 1 depending on whether indices fit or not. Meaning you put I here, J here, and you have ij connected by strings now. So if all the strings join equal indices, it's okay. Kronecker is 1. If not, it's 0. So this is quite interesting. I mean, yeah, these are the simplest quantum groups. And what we did last time, we said that, well, O and UN are definitely easy by the Brouwer theorem, D being the pairings in that case. And ON plus, UN plus are also easy. What's the category? Well, you have to remove the crossing A, B is BA. So finally you get the non-crossing pairings. So that was the theorem. ON, UN, easy. With pairings, well, pairing some colored for ON and matching somehow for UN, and same thing for ON plus, UN plus. Very good. So I have this notion now. We concluded that somehow we have to look at quantum permutations now, because well, this was for partitions. So all these examples that we had are with pairings. So more about the easy quantum groups corresponding to P itself, the category of all partitions, or to NC, the category of all non-crossing partitions. And this, well, this will be Sn and Sn plus, the permutation group, and it's free analog. So that's why somehow this, the present lecture continues naturally what we did last time. On the other hand, I mean, quantum permutations, yeah, that's just obvious. I mean, quantum groups, quantum permutation groups are just appear all the time. So I have to see if we have quantum analogs. So independently of this Easiness business, that's what we will do actually. That's how these were found by Suzu Wang 20 years ago. Let's just see what happens. So we'll see that this exists indeed. Then we'll prove that they are easy, and with that we'll do some advanced algebra and analysis. Then once you're done with permutations, you want to go one level up to reflections. So we'll do that a bit. Quantum reflections, and finally we'll talk about arbitrary group of quantum permutations, so subgroups of Sn plus, and a few techniques there. Transitivity, that's something quite recent and interesting. Orbits, orbitals, also some planar algebra work, which is interesting. So this will beat many things of all kinds of algebra analysis, and so this is somehow discrete. What we do today, last time it was continuous. There are somehow done with the main example, main things to be done, and the next lecture will be about things more really more advanced, like maximal tora and their use in all these questions, also matrix models. So really it will be one level up in the last lecture. Okay, let's have it started now. So how to define quantum permutations? Let's look at Sn. So in our case here, all the groups are algebraic. So we'll look at Sn as permuting the coordinate axis of Rn. These are so-called permutation matrices. So like 0, 1, okay? And what are the coefficients of a permutation matrices? It's exactly this. It's a Kronecker somehow. It's 1 if sigma of j is I and 0 otherwise. I mean, it's a characteristic function if you want. Now, well, for liberating this, the trick was to look at the relations satisfied by these guys and then remove the commutativity. So what are the relations? So these things are characteristic. They take values 0 or 1. So there are projections in the sister algebra sense, meaning P is P star and P squared too. And also, if you look at this matrix, if you keep I fixed, J varies, the sum is 1, right? You can see it on permutation matrices. I mean, exactly a 1 and the rest is 0, so the sum is 1. Trivial. And same for the columns. So, well, that's pretty much it. I mean, now if we call a matrix magic, matrix made of projections with some ones on each row and each column, that's your definition of Sn plus. So take the universal sister algebra generated by an n-time n magic matrix. So this looks very good. First, you have to verify the axiom. So that's once again routine, exactly as in the continuous case for when plus un plus. So you have to map the uij's to some guys. So somehow you have to map u to some matrix. And the point is that if U is magic, this matrix is there that you need for delta epsilon s and magic too. So same proof as for n plus n plus. It's really simple. Now, well, we have as well an alternative definition. So this was with when Sn regarded somehow as an algebraic group, but let's do it with permutations too. So Sn is the biggest quantum group acting on one hand, right? And is that true for Sn plus? Not really. There's a bit of a surprise here. So if you try to construct the biggest quantum group acting on one n, it doesn't exist. I mean, there's no universal object. And the reason for that is really bizarre. I mean, it's a non-commutative thing, is that there are many quantum groups acting on one n, and many of them don't leave the counting measure invariant, if you can imagine that. So of course, a group acting must leave the measure invariant, right? But in the quantum group case, it's a bit technical and it's not true. So somehow for any measure, there is a universal object leaving the measure invariant on one end. It's completely bizarre. Discovered by Su Wang. So yeah, that's our first difficulty. And how to solve it? Well, you assume that it keeps the counting measure invariant. So that's the theorem. If you go for the proof, it works. So acting means that you have something like this. Okay, g cross x to x, well, abstractly somehow. Now, in functional analysis term, you have to reverse the arrow. So you need a map from here to here, so from C of x to C of j tensor C of x, called coaction. Okay, so it must be co-associative, something like that. And now if you, well, C of x is just Cn, right? So finally I have a map from Cn to C of g tensor Cn, so it's a matrix, right? If you take the standard basis here and here the Dirac masses, you get a matrix here. It's given by a matrix. These are the so-called coefficients of the coaction. It's a matrix. And so already the general theory tells you that this must be a co-representation in order for this to be a coaction. Now in our case, we have C of x, right? So it's special. And it's an algebra here. So commutative and everything. And in addition, we have this measure which must be invariant. So if you work out all the relations, you reach to the conclusion that in order for this to happen, you must be magic. So we're done. I mean, having a group acting on X, quantum group means to have a magic matrix. So the biggest one is Sn plus. Very good. So what we have here finally, there is two definitions of Sn plus, which are both good. So one is this. This is probably the simplest, right? So you should just take this and that's all. And this is somehow a theorem, but you can do it in the other sense. I think, I don't remember in Bang's paper, I think it was in the other sense. Somehow that's the, but this is more tricky, I mean, because of the counting measure. No, definitely, I mean, that's the good definition. At least the modern definition is like this. So you see here, you don't run into that difficulties there with the measure. It's just very straightforward. Yes, always. Actually, that's something that we'll do for other groups too. Always look at groups, even the simplest one, like the cyclic group, to look at them as algebraic groups. You see the cyclic group, for instance, take coordinates of R and you permute them in a cyclic way. So it's always, yeah, it's always good to look at groups, even if they are very simple, as algebraic groups. And that's an example here. You see, algebraic, no problem. As a finite group, somehow it's more complicated. Okay, now let's go to some basic properties. So first, do these beasts really exist? I mean, maybe we're just wrong and Sn plus equals Sn, right? That's not clear. We have to check it. And well, we have a quotient map, of course. So we have an embedding now. Is this an isomorphism or not? And that n is 2, it's an isomorphism because if you think at a 2 by 2 magic matrix, the projection sum 1 must be of this form. So then it is commute, obviously. So we're done. It's commutative, everything. At 3 is the same thing. So it's a good exercise there, actually. Take a 3 by 3 matrix formed by projections, sum 1 on each row, each column. Must prove that everything commutes. Exercise. Okay. And, now at n is 4, this is different. So you see, if I just concatenate like these two matrices that we had before, remember these matrices here with P1 minus P. So I do this, but for the first one, I take it depending on P, the other one depending on Q, and PQ is somehow free, I don't know, some Hilbert space. So this will be magic, of course. Now, PQ, of course, can be chosen not to not commute. This means that S4 plus is different from S4, right? Because it must be non-classical, the algebra being non-commutative. Also, you can choose if we want PQ to generate an infinite dimensional algebra. This means that C of S4 plus is infinite dimensional, so S4 plus is infinite. So this is quite interesting. I mean, quantum permutations exist starting from 4. They are non-classical and infinite. You see how you have your 4 points there, and yeah, that's life. There are an infinity of quantum permutations of them. Very interesting. Of course, this remains true at n greater than 5 because I can always add here a tail of 1s. It stays magic. So very nice. This exists starting from 4. Now, the problem is the proof here is somehow, yeah, can we better understand this proof here, what was going on here? And this is quite tricky. So, well, we can use group duals. So the idea is that, remember, S2, S2 plus makes things collapse at 2 where they are equal, and that's the cyclic group. And if you want, it's the dual of itself, just trivialities here. Now, with this point of view, remember we had a notion before of a dual free product. So somehow the idea is that the dual free product of S2 and S2 embedded into S4, but let's do it with this group. So the idea is that what we did before the concatenation produces a copy of this free product of Z2 and Z2 inside S4 plus. Well, you don't need all these things. Maybe these are a bit too abstract. You just take this guy here, and it's represented like that. Okay, you just have to find PQ in the group algebras there. The sum of generators, very simple. So yeah, so that's an explanation for this. You see, I mean, this is definitely infinite. So you can understand why S4 plus is infinite because it contains this infinite guy, which is actually, that's something I hope you know, that's the diedral group, the infinity, Z2 free product to Z2. And actually even better, you can prove that this copy here, so we're done with the question here, we understood. Actually this guy here acts on the square. Well, we'll get to this later. So it's even more interesting than that. Now, well, so I understood why this is true because we have a group dual there. At least we have some understanding of these group duals. But can we understand now what S4 plus is itself? And well, the answer is very strange. So it's actually a twist of SO3. Once again, very bizarre things right from the beginning. So the twist of SO3 is constructed like this. It's a bit like SO3, 3x3 matrix, orthogonal. Then, well, you have to put some minus sign somewhere. That's always the idea of twisting. You put anti-commutation in certain places instead of commutation. And then the determinant must be 1. And here you remove the signs because the signature, because the signs are already here. I mean, if they anti-commute, there are some signs somehow there. So this is your quantum group. And now the very strange thing is that this is the same as S4 plus, so here's the isomorphism. I mean, I take this matrix here, 3, 3. I add the trivial thing there for it to be 4, 4. And I conjugate by this matrix, which is, this binary matrix is the Fourier matrix of the Klein group. And this must be magic. I mean, these relations here for SO3 minus 1 imply that this guy is magic. Vice versa, the magic condition, if you conjugate it by the same Klein thing, you get to a matrix like this with zeros 1, and this corner here, 3, 3, must satisfy exactly this. So it's somehow you have arrows in both senses. That's your proof, which is very strange. So, well, it's scary. I mean, how can we survive? It's yeah, how can I understand this? I mean, very complicated. Well, answer comes from Easiness. Okay, Easiness will eventually lead to an understanding of this. Okay, so it's powerful Easiness. This thing here, look at it. No way to understand this, and with Easiness, it's gonna be easy. So let's do that representation. So well, the Tannakian category, first for Sn, that's a very classical thing. It's easy generated by our partitions. That's a standard thing. And well, these are the linear maps as before, the definition of easiness. And what's the reason for that? Somehow, well, all these things are invariant on the permutations. Let's put it like here, like that. And for Sn plus, well, the Faraday's in general, when you liberate, you have to remove the crossing, so you can only get NC, all the non-crossing partitions. So that's our theorem. Sn, Sn plus are easy, coming from P and NC respectively. Yeah, let's see how the proof goes. So for Sn, I was saying that everything is invariant on the permutations, but yeah, you can get it like this, or with Brouwer. We already know the Brouwer theorems, right? For N plus, Un plus, we did that last time. So getting it from Brouwer, what's the point? So Sn is contained in On, right? So we first have to write a formula of this type. To find the ideal here. And if you think a bit, the ideal comes precisely from this intertwiner here. Ei tensor J goes to delta Ij Ei. So and this is actually exactly the intertwiner given by the Umbro partition with two legs like this and like this, like kind of fork with two branches like this. And yeah, something like a Y, let's say, a Y partition. Okay, so now I have this formula. So at the level of Tannakian categories, remember things go in the other sense. So if you take a subgroup, the category will get bigger. So the category for Sn will be the one for On, which are just the pairings. And you have to add this Y thing. But it's clear with the Y thing, it has 3 legs. So if you put Y's like this, you get how many? 1, 2, 3, 4 legs, 5, 6. You can get partitions with arbitrary number of, well, you get all of them, okay? Very simple. For Sn plus, now same thing. So you do the same thing with your Y, but with the non-crossing pairings as input somehow. Take all the non-crossing pairings, you add your Y. So things will stay, of course, non-crossing. and you get all the non-crossing ones. So that's the proof of this theorem. Now, as an application, yeah, this gets us into SO3 right away. So the fusion rules are the same as for SO3, so these are the Clebsch-Gordon. But the dimensions, of course, they change because, yeah, well, the fusion rules, you see, there's no end there, so it must appear somewhere in the dimension. And here's your formula, some Q numbers over here. So how to do this? Well, I told you before, that's why we're computing these tensor categories, because once you have the category, you have everything. So let's see an example of this. So I know this from Easiness. Now, if you want to compute, for instance, the character, the law, the moments are just have to come partitions. So there are the number of non-crossing partitions of p points. That's well known. That's Catalan number. Now, we're getting here into probabilities. So as last time, yeah, you have to know, or otherwise you have to work it out with still just. So, well, here, of course, we know. So, I mean, at least I do know. So, I'll tell you without still just with the physicist tricks. So, we're here. We have a measure having as moments the Catalan numbers. And what do we know about this Catalan is that if you take the semicircle law, this has the odd moments are 0 and the even ones are Fuscatalan. So this measure is somehow the square of a semicircle, all right? And we're done, because for SO3 is the same thing. Well, we're not done yet, yeah. So that's one thing, it's a square of the semicircle somehow. Now the point is that, and here comes my physicist trick, that for SO3 you get a square semicircular law too, because SU2 is a double cover of SO3 somehow, and SU2 is the fourth sphere, the real, and well, you look at here the character of SO3, you can see two the spheres. The character of the fundamental representation of SU2, it's a semicircle on that fourth sphere, and yeah, in 4 dimensions. I mean, the sphere is 3 dimensions, the sphere itself. So the character of the fundamental representation is a semicircle. Now for SO3, the fundamental representation is the adjoint of the one of SU2, which means squaring the character. So yeah, we lead to the conclusion that chi for Sn plus has the same law as chi for SO3. And everything depends on chi, right? So you get the same fusion rules as for SO3. Well, this is a bit tricky. Of course, you don't need to be at this level. So once you have this, so this is just a count here, okay? Counting partitions. It's Catalan. That's very easy by recurrence as usual. Now, once you have this, you do your combinatorial. You should prove this by recurrence. That's it. Well, as a comment, yeah, well, this is actually wrong as stated. So 2 is 3 doesn't work, right? Because these are Z2 S3. So it's only starting from 4. And the reason why, first the mistake is when we counted the partitions. The mistake is here, actually. This only works for n greater than 4. And well, if you want an explanation for this, that's a Jones index somehow. We'll be back to that later in algebra. So we have to count these guys. No crossing pairing partition of these things. Now by fattening somehow. Well, I have to know, for those who know, by fattening is the same as pairings of 2p points. The 2p points, I can rotate them like this, and I get a so-called tempered leaf diagram. And these are the Jones thing, and it's well known that they are not faithful unless the index is greater than 4. Okay, so there's something technical here. But as an interesting remark, everything is simpler than for Sn. Remember, so what did we find finally? Yeah, Clebsch-Gordon. I mean, these are the simplest possible rules, right? For Sn, you get all these young tableaus and all that, little Richardson. I mean, it's terrible. Here, the combinatorics is trivial. So, yeah, very interesting. So finally, You see the analogy between S and Sn plus. In the beginning, it was bizarre and got very hard with that SO3 and the infinity. Now Sn plus is becoming simpler. It's going to be like this all the lecture. I mean, it alternates. Some things are easier in the classical case, some other in the free case. It's a bit mysterious. But here, definitely Sn plus beats Sn. I mean, Clebsch-Gordon is much simpler than all these young tableaus and stuff. Now, let's do some analysis. So let's, we already saw character here, square, semicircular, but let's try to understand that a bit more. So let's go back to Sn. So as the main of the character for Sn, first of all, Sn acts as permutation matrices. So the character is the number of ones on diagonal, and these are exactly the fixed points, right? So the character is the number of fixed points. So the conclusion is that, well, let's try to understand when a permutation has no fixed points at all, right? That's the very first question. That's with inclusion and exclusion, I guess. I guess you know this thing. And you get 1 over E. Oh, maybe let me tell you, however. So what's the inclusion and exclusion? So that's your symmetry group Sn, right? So to compute permutations which have no fixed points. So inside the symmetry group, you have those fixing 1, those fixing 2, those fixing 3, and so on. You have these subsets. You want to compute the complements. And here comes your principle. So it tells you that in order to compute these complements, take the big set, that's factorial n. You remove all these guys. These are n minus 1 factorial each. But then if you remove the intersections, you have to put them back because you remove them twice. And then the three intersections, you have to put them back and so on. It's an alternating sum. So if you work out the cardinalities, you get exactly this. That's a series of 1 over E. Then goes to infinity. So as the measure now, which measure on the integer starts with 1 over E? Poisson law, of course. So by modifying a bit all this, you get Poisson, okay? Here you just compute the probability at 0. You can compute probability at any k, you get the density of Poisson. So that's your proof. So very interesting. When n goes to infinity, the number of fixed points of permutations becomes Poisson. This is the foundation of all probability on groups. I mean, this is an extremely important result. Okay, it's also very cool. I mean, you get 1 over E, right? This is quite remarkable. Now, Sn plus, well, we should get some kind of free Poisson, right? So in order to do that and more, let's do some theory now. Let's go back to the arbitrary easy quantum groups. These come from partitions. So one interest in studying them is that you can integrate over them in a very explicit way. So how you do that? You take, you want to integrate an arbitrary product of coefficients. Now, if you take all these integrals all together, by Peter Well, they form the projection onto the fixed points. But the fixed points is spanned by partitions. So you get the formula in terms of the gram matrix of that fixed points. If you compute that gram matrix, that's it. It's n to the number of blocks of the join. I mean, when you put the partitions together. And the formula, to be precise, that's the gram. You have to invert it. That's the so-called Weingarten matrix. And you just sum the entries of the Weingarten matrix with this. These are the usual Kronecker symbols, okay? Index plugged in inside the partitions. So this is very beautiful. I mean, well, of course, this is in a real case, in a unitary case, and that's some exponents, and there are variations to, for instance, a symplectic group is not easy, but almost. So it's a very wide thing. This is due to Benoit Corris and his friends. This formula was nearly for classical with me in the free case, and well done some others. Then Bichon, Speicher, Curran contributed a lot to this too. Right? It's essentially Collins who came up with this idea. And it's extremely useful. I mean, in a classical case, if you do random matrices, you want to integrate over y and un, that's what you use. Okay, it's not a quantum group thing, it's a physics formula for integrating. And in practice, you plug this into your laptop, and laptop computes this, and you get the result, and you publish your paper. So, okay, so it's like engineering. I mean, they call it Weingarten calculus. This thing is extremely powerful. Anyone can understand. So now back to our characters. Yeah, this of course can do anything. So here's the first result. So let's do it at the same time as an Sn plus. For Sn we get Poisson. For Sn plus, if you compute this kind of squared semicircle that we have, we get this. And this is the so-called Marchand-Pastur law from free probability, which is also called free Poisson. So there are three names actually. Square semicircular, Marchand-Pastur, free Poisson. And why free Poisson? This would be the most convenient for us because here we have Poisson, right? Because Poisson appears via Poisson limits theorem, and this guy appears via free Poisson limits theorem in the sense of Voigt-Kulesku's free probability. But that's just a comment, we'll not get into these details. What was the proof? Actually, here you don't even need Weingarten. So integrating the character means counting the fixed points, so counting the partitions. And it's well known that the partitions are the moments of Poisson, the number of partitions, and here we get the non-crossing ones. So standard probability. Now, more interestingly now, if you take the truncated characters, truncate with the parameter t, we'll see in a second why this is important, we get Poisson of t and Marchand-Pastur of t, or free Poisson of t if you want. Once again connected via Poisson free Poisson limiting theorem. So here, well, the Peter-Weyl trick doesn't work. This is not a character, so you have to use the Weingarten formula in order to integrate the powers. That formula over here. So yeah, you get some sums, whatever you approximate when n goes to infinity, and you get this thing here. So with respect to this previous slide, here it was just number of elements of decay. Here, for each element of decay, it contributes to t power the number of blocks. You see, when t is 1, you get the same thing. Once again, standard probability will get this. So this is very interesting philosophically because you see finally the analogy between Sn and Sn plus. Yeah, that's best understood via easiness. We know this phenomenon then is 2 and 3 where it collapses and then it becomes SO3 and all that. That was totally ununderstandable algebra. Now I have something very conceptual, so which works well when n is generic, where it goes to infinity. I mean, right? All this easiness things you see here everywhere. It's n goes to infinity. So easiness, yeah, that's the scheme. So these are my things and categories of partitions. Here we have Poisson free Poisson laws. And it's important to have t because in free probability, the bijection, there's a bijection between classical and free laws somehow. But it's not between laws, it's between one parameter semigroups depending on t. That's the so-called Berkovich-Pata bijection. And that's why we need the t from this diagram to be complete. So this is a Berkovich-Pata. This is just adding the crossing, removing. And here, well, from Sn plus, you get the classical version. In the other sense, you do this thing, removing the commutativity, just keeping the magic condition. Well, of course, there are many other things like planar algebras, algebraically, and also a lot of Diaconis type mathematics, probability. So let's not get into this. Let's look. So I think that's pretty much, yeah, that's pretty good as knowledge of Sn plus. You can of course do many things afterwards. But now let's get to other quantum permutation groups, I mean subgroups. So the simplest thing is to construct you take a finite graph, you take the quantum isometry group of it, which means you just assume that the fundamental representation commutes with the Laplacian or adjacent symmetrics. So you get a diagram like this. So symmetry group, inside is the symmetry group usual. Here is the free symmetry group, and quantum symmetric group of the graph. First example, if the graph has no edges or edges everywhere, you get Sn plus, of course. Now, more interestingly, let's take the cycle graph, just like this, okay? So here do some algebra, you get that this has no quantum symmetry in general. I mean, you get the classical group, which is the diedral group, right? Unless at n is 4, where a bizarre thing happens. So let me show what's going on. So C4 was the 4 cycle is the square, okay? But not the square, you have this complementation operation. If I take the complement of the graph, which means the two diagrams, of course, the quantum geometries might be the same. So I have the two squares, the two segments. Now the two segments I can we're not doing geometry or something. I can put them like this. And the thing is that remember the diagonal trick for proving that S4 plus is infinite. These matrices. It's clear that it works here. I mean. That the diagonal matrix that we constructed, block diagonal, it will act here. So you get this, okay? The infinity dual actually acts on the square. That's something I told you before. So it's infinite, okay? It's not, it's a bit bizarre. So if you take these cycles, every time is the end, the exceptional thing happens at 4, okay? Once again, a bizarre thing because I told you before, starting from 4 joint index, things go fine here. Yeah, that's an example where precisely at 4 it fails. So a bit strange, these things, a lot of algebra. So the question was the symmetric group of the graph. Yeah, we can become obsessed with this question. And the square, and well, simplest idea is to as the square as particular example of a cube. I mean, it's 2 dimensions, you have the cube and so on. So let's compute that series. Maybe it belongs to that series and it's fine. And if you do computations, you reach to another bizarre thing that g of the cube is on a twist of n. So in particular, at n is 2, you get to 2 minus 1. So I have our answer for question. Goods. But this is still not okay. Okay, many surprises. Because now I would like to say, you see, for the cube, the symmetric group is the hyperoctahedral one. So I'd like to say that, well, Hn goes to n minus 1 should be a liberation. And this can't because the character law for twist is the same as for untwist. So you get a Gaussian law there, and this cannot be analog. For Hn, it's a kind of modified plus 1. So modified plus 1 cannot go to infinite probability to a normal law. So this result is true here, but it's not. It doesn't produce the free analog of Hn. So we're getting now into another obsessing question: what is Hn plus? And here the idea is the following. So Hn is the symmetric group of the cube, but it's the same as the symmetric group of the coordinate axis in Rn, right? If you rotate this axis, the cube will rotate too. Now, well, if you have the axis, you just can put segments there, minus 1, 1. So it's the symmetric group of n segments. And that's the correct definition. If you take the quantum symmetric group of the n segments, you'll get your free Hn group. To be more precise, so in the classical case, symmetric group of 2 segments is Hn, that's what you're saying. That's also a Breeze product if you want. And it's easy correspond to the partitions with even blocks. Kind of same proof as for Sn, you had some signs there. And that's why blocks must be even. Now Hn plus, this was a theorem here, okay? Very simple. Now Hn plus, you just take this and you say that's your definition. So to be more precise, well, you have to prove this. So it's a so-called free Rees product in the sense of Bichon. Not very complicated. And that's your definition of Sn plus. And then with the standard technique, I mean, basically from here you have to remove the crossing. You get that it's easy in the category with partitions, no crossing with even blocks. Well, now, so we have Sn, Sn plus, Hn plus. Let's go for more general reflection groups now. So if you take, yeah, there's a whole story here. There is a series with 2 parameters. So just add the parameter S, which is at 1 is the symmetric group, and at 2 is the hyperoctahedral group. So it's this Rees product here. You see, I adjust these formulas here just copied from here. I'm adding an S parameter everywhere. Instead of a cyclic group Z2, I mean all these signs, for hyperoctahedral, I put as yes, roots of unity of order S. And you get basically the same thing. You have some, take copies of the simplex, and that's a product, risk product, which is a reflection group. It corresponds to partitions satisfying this technical condition in each block. White is black modulo S. Now, as before, liberating that your definition, there are some things to be proved. So this is very interesting because you see we enlarge our list of easy quantum groups. So we have SN plus, S is 1, S is 2, HN plus, and so on. S is infinity, of course, these are no longer permutations, so this is a bit special. And these are called KN plus. Well, these are the big things somehow which contain everything, so they're very important. That's why they have a special name with K. It's the complex reflection group and it's free analog. There are a lot of very interesting results here, free probability, all that. So that's if you want to read about this, it's what is it? My paper with Belinsky, Capitan Collins. A lot of probability there called free Bessel laws, and the one with Vernier, like fusion rules for quantum reflection groups. These are the two papers in the beginning. Then there are many of them. If you are not happy with this reflection group, there are many more constructed by Raum and Weber. There's a series of papers on classification of easy quantum groups. In the real case, in the complex case, there is ongoing work. They're writing many papers. The guys there of Moritz in Saarbrücken. So yeah, a lot of things going on here. Both probability, algebra, everything. That's somehow the hot subject in quantum groups, complex reflection groups. Oh, well, this was nice, but a bit specialized. So I told you in the beginning, the end was of the game was to look a bit at subgroups, and we got finally into the specialized thing. So let's relax now a bit and try to understand general techniques. So what do you do with the permutation group? You look at orbits, right? So this won't really work exactly. There are some subtleties here. It's quite recent. So that's an old definition due to Bichon, means zeros. So transitivity, that's the first thing before orbits. It's transitive when the coordinates are non-zero. In the classical case, you see, this is non-zero, means that it's transitive. But the problem is that, everything is transitive, right? All these guys that we considered. So very good, that's something satisfied for everything that we constructed so far. Now let's understand orbits, the transitivity. So, well, it's obvious, I mean, can only be this, right? Because transitivity was Uij different from zero. So normally the equation is this, and the three conditions for an equivalent relation come exactly from delta epsilon s. So here's your proof. The problem is that what to do with this, because we have zero examples, right? Remember, they're all transitive. So who introduced this? Well, it was also Bichon in the same paper, and he actually did something very interesting there. So it's called algebraic quantum permutation groups, and with zeros, I think. He classified all the group dual subgroups of Sn plus. So what's the idea here? Well, that's a statement. I mean, this must be duals of quotients of product of cyclic groups, then one for a partition of n. So in one sense, well, you have these Fourier computations here. Maybe let's not get into this. Let's get in the other sense. Yeah, let's take gamma inside Sn plus. So we use orbits, okay? This must have orbits. So you take n is n1 plus nk orbit decomposition. And the idea is that gamma somehow must appear from blocks of size n1 and k. Everything diagonalizes, and that's how you get your cyclic groups here. So very interesting results, application of the orbits. Now the problem is, can I get beyond orbits like orbitals? And the first remark is that the equivalence relation, remember, how is it? I is equivalent to j, the same orbit if the coefficient is non-zero. if in the classical case, it's this. I mean, the k orbitals, level k orbitals, it's this, right? Now in quantum groups, we'll take the same definition. So is this an equivalence relation? And remember the proof was using delta epsilon s. So the epsilon s is not a problem. The argument extends, so again that it's reflexive and symmetric. But the problem is with transitivity, which was coming from delta. So here it's tricky. At k is 2, that's the trick, which is, I don't know, 3 or 4 years old, discovered by Lupini, Manchinska, and Robertson. Also Mustoriter Verdon in some related work. So it has 3 lines, but I have to be clever to find it. And so there are orbitals at 2 orbitals. In case 3, this fails. You don't have a trick, and actually, well, there are a few things which holds. In that case, 4 totally fails. So this doesn't work, but it's not a problem. I mean, if you do group theory, usual group theory, usually transitivity, I mean, some orbits and sometimes orbitals, but unless you're very specialized, you know, it's orbitals. But there are some questions here interesting. Yeah, what are the things which do hold? It's a bit technical, or this is related somehow to partitions, and if you do some probability, and the idea is that partitions with 3 points, they're all non-crossing, right? Partitions of 3 elements. The crossing starts at 4, somehow. That's why I want to see are a bit related from a certain point of view of probability, because things are non-crossing. And here with the crossing, it is very different, classical and free. So anyway, there are these theories, and very useful for what these guys are doing, quantum information theory, Lupini, Manchinska, and the others, Robertson. So a lot of applications here, recent work, very interesting, these notions. Now, let's finish with some algebra. So quantum Cayley fails. Very interesting result by Sonia Natale in a paper with me and Julien, which is very bizarre. So remember Cayley, right? If a group has order n, it acts on itself. It's a permutation group. And this doesn't work at all. I mean, it cannot produce that magic thing. And there are actually, that's, if you know finite quantum groups, as Sonia does, she's classifying them, right? And the guys in Argentina there, yeah, she has an example of finite quantum group having no magic representation. So this is very strange. And, you see, I mean, it's different from a classical case. In a classical case, permutation groups are inside finite groups. Here it's not like this, it's different. Theories are different. No one is included in the other. So very interesting. And by the way, a problem here, I mean, there are so many things, people working quantum permutations, there's a lot of work, but on finite quantum groups, not that many. So when I was telling you about Sonia and the others, they're rather in quite often over fields of characteristics 0 or even arbitrary. So in this setting here, sister algebras, everything, things are not that much developed. And that's one thing to be done, yeah. Finite quantum groups, okay? Not the same thing as quantum permutations. Now, this was a negative result, so do we have something positive too? And here is the result that's all stuff by me 20 years ago. So these fixed point spaces, we know that they form a tensor category, well, the home spaces, but by Frobenius is the same thing. Now, something much more powerful is that they form a planar algebra in the sense of Jones. What's the proof of this? Well, you need to know what a planar algebra is, and I won't tell you now, it takes a long time, but it's basically something much more powerful than a tensor category, because a tensor category has just a few operations like composition tensor. In planar algebras, we can compose things like you plug them into boxes and you get other things. It's a very, the most general possible planar operation formalism, an infinity of operations. So that's your result, very useful. And well, of course, this connects, right, what we're doing here, subgroups of Sn plus with what Well, people in planar algebra, these appear as very special planar algebra, so-called spin planar algebra. So this connects common permutations to a small part of planar algebras. But this is a very interesting connection from both sides because it makes correspond a lot of things like Sn plus, temporary Lieb, Hn plus to Fus Catalano, Vincent Jones. These common automorphism groups of graphs I was talking about correspond to the two box things of Vincent Jones. Somehow the Laplacian is in the box. So there are many interesting connections of all this. For instance, all this work now by Simon Schmidt and the others, computing the G plus of X is that's very advanced. For instance, with respect to Vincent Jones and Liu are trying to classify these things in general, not in the spin case, by using some kind of bounds of the dimension. So yeah, all this is very interesting. Finally, yeah, let's end with this. And it's very beautiful. So there's nothing in between Sn and Sn plus. Why? Because of course no groups right above Sn, no group duals by Bichon. There are also no easy quantum groups because this would mean to have a category of what of partitions between non-crossing and all, and there's nothing. It's a simple proof there. Now at n is 4. At n is 4, remember, S4 plus is SO3 minus 1. So this means that you can classify all those groups, right? They should be subject to something AD. You can classify them and there's nothing between S4 S4 plus. Now at n is 5, you can go to this work of Morrison and the others. They just classified subfactors of index 5 in a series of like this of papers. You check what they did and so the solutions. And yeah, there's nothing between S5, S5 plus. So I'm using here, of course, this duality here, this kind of correspondence. So and that's very difficult. I mean, their work Morrison and the others are very sick, so you have to do all that, and you write one more page, and it's over for permutations. So yeah, very good conjecture. Sn inside Sn plus is maximal. That's well, that's kind of doable. I mean, we can do some combinatorics there. So I'm telling you, it's partitions finally, and it's a good introduction. I think everyone who started to work on quantum permutations, at least for those I know, struggle a bit in the beginning, try to put this conjecture. That's a standard exercise for someone starting. Yeah, if you want to get started, yeah, try this. And there's a lot of fun. I mean, you can try to use your computer, things like that. Maybe you'll get it. I don't know. But it's a very good problem, yeah, for understanding what are the difficulties and why not producing an excellent paper. Who knows? Very good exercise. So that's pretty much it. We have a very nice theory. And of course, this is very hot. I mean, things are recent here. It goes in all senses. So in the last lecture, he says, obviously, think of this. Here, just go to research. I cited so many people, so all these guys know. Yeah, there are also more like Fred Lombran and McCarthy, who else, Kirvasitu, all these German guys around Weber, and I don't know many more. Forgot now. Late at night, Pavel Josiak also. Yeah, many people. Sultan, of course. Students of Bishop. Okay, let's stop here. Yeah, we will find them. Okay, go to blogs, whatever, you will find lists. And yeah, next time we'll get away from this, which is technical. We'll get to maximal Torah and models. Okay, guys, hope you like it. And yeah, quantum permutations are the best. Hope to see you soon there. Solving maybe this conjecture Sn inside of Sn plus maximal. Very good question.